afternoon. Welcome, everybody. Welcome to today's Liftoff webinar, and thank you for joining us. My name is Christine Longroy, Vice President of Business Development here at LIFT. LIFT is the National Advanced Material and Manufacturing Innovation Institute, headquartered here in Detroit. And as a public-private partnership, we're focused on strengthening the defense industrial base, connecting, convening government, industry, academia, where we are advancing manufacturing through technology and talent development with the core mission of ensuring the transition, scale up, and fielding of advanced materials and manufacturing process to support our nation's economy and security. Today, I'm honored to host one of our own, Dr. John Keogh, VP of Technology here at LIFT, and he leads all digital and physical aspects of engineering here. He's going to be sharing his insights on hypersonic materials and manufacturing, accelerating the next-gen defense capabilities. It's a critical area of focus here at LIFT for us, and we are redefining what's possible for the national defense. So during the webinar, please, if you have questions, go ahead and put those in the Q&A. We'll take those at the end. And we are going to be launching some polls throughout, so make sure that you're prepared to answer those polls during the session as well. So, Dr. Keogh, take it away.
Thank you, Christine. I appreciate it.
Yeah, no problem. And I'm going to launch that first one, so take it away, John.
Okay, you got it. And thank you for everybody joining. One quick correction, I am no longer responsible for all things digital and physical at LIFT. Actually, that's my colleague now, Nick Johnson, VP of Engineering. So I am VP of Technology. I help to lead the tech portfolio at LIFT now. I've been with LIFT for roughly 8 years, but my role is changing, and so I have to give it to Nick. He's fantastic, does a great job, and so the digital and the physical now resides under him, and God bless him. So like I said, thank you for everybody joining. We've got some interesting content and material to discuss today. I think you've already seen the title here, but the intent really is to discuss and frame up not only a quick anchor point as far as who we are at LIFT, what we're doing, why we care about hypersonics, why is it a unique and interesting challenge relative to, say, other environments or just normal supersonic flight, things like that. How we go about problem solving at LIFT and how that approach and our associated differentiating capabilities are leveraged against solving problems for materials and advanced manufacturing in the setting of extreme environments or otherwise. We'll then roll up with an example project that shows kind of how the digital and physical activities at LIFT tie together from end to end, and multi-length scale, multi-time scale, full digital thread type approach all the way through performance modeling, and then we'll just tie it all back together again as far as call to action, how it all interfaces and integrates with our efforts at LIFT, and then we'll land with the Q&A. So we've already seen this here, but we're talking about hypersonics, we're talking about materials, manufacturing, solving problems that are difficult to solve. Very exciting topic. It's a lot of fun to talk about, a lot of fun to riff on and discuss, but it's also critically important, right? So that said, I said we're going to give a quick anchor point on LIFT. Here we are, right? That's our beautiful headquarters in Corktown, Detroit. You can see the big buildings in the background. There's actually Canada over the river there. And Christine already said, all of this, but really our core charter as an institute, as a public-private partnership, is to drive American advanced manufacturing into the future through tech and talent development. And we do that in the context of materials, manufacturing processes, systems engineering, and again, talent development. I like to think of LIFT as sort of a cross-cutting institute as well. When you focus on materials and manufacturing, nothing's off the table. So we're not the Robotics Institute, but we use a lot of robots. We're not the AM Institute, right? We're not American Makes, but we use a lot of additive, and so on and so forth. So we actually cross-cut and co-integrate a wide range of different technologies to solve complex problems. And one of those problems, of course, is materials and manufacturing for hypersonic applications. A couple of figures of merit for LIFT as well. You see that big facility. We're not just doing program management. It's again, I said 100,000 square foot facility. We have roughly a $60 million investment in advanced manufacturing capabilities that allows us to do very interesting things in the setting of metals and ceramics and their composites testing and so on. Currently, we're running around 30 active programs, distributed anywhere between directed type projects or programs, direct internal programs, project calls, and so on. There's a wide range of activities that we're constantly engaging in. And we also have talent operations in 25 states. And I think, many of you, if not all, already kind of know all this, but just wanted to bring it to the top. Christine mentioned the public-private partnership. This is just a selection of our member base and some of our key stakeholders. I think we have over 420 members right now. On the industry side of things, we have global corporations, U.S. headquartered, but global corporations, all the way down to single-person companies, wide range of academic partners, and then of course a whole bunch of our loving government partners that we're honored to serve and do good work on their behalf. So speaking of the government, what's their view of us? Like we were stood up by the federal government for a reason, and it's kind of captured on this slide here. So when you look at this, the bottom there, kind of close to the bottom, you have this MRL scale, manufacturing readiness level, and there's also a TRL scale. We'll ignore that because it kind of runs ahead of the MRL scale, but in the MRL 1 through 3 space, you kind of have basic research, where a lot of good ideas are nucleated and are born. And then on the 8, 9, 10 space, you have pilot capabilities all the way into full rate production. But you have what we call this valley of death in the MRL 4 through 7 space, and that's where we live. We're meant to serve as a bridge or a springboard to help transition technology into the full-on adoption and transition arena. But the way that we act on this this graph, or kind of just the fact of the matter, our charter, you have to have a problem to solve. It's all too often, particularly in the setting of advanced manufacturing, that you have a cool solution and you're searching for a problem. The law of the instrument says that to a hammer, everything looks like a nail, and we have to be careful with that, right? So we look to, say, the 8, 9, 10 space for a real problem, or the national defense space for a real problem to solve, and then we look back and reach back into the 4 through 7 space to find solutions that are ripe for carrying forward, developing, and transitioning into that handoff. And you'll notice that MRL 8 chevron is blue as well, because we can't just stop at 7. We actually have to have a handoff into the 8. So really, we're 4 through 8. And again, this is all done in the setting of advanced materials manufacturing, systems engineering, talent development, and really to enable kind of all those bullets that you see there on the right: tech transition, lowering risk, scaling, access, and serving as an ideal partner. But that's kind of our reason for being, if you will. Now, the reason we're here, though, talking and spending our time together, is, as I mentioned, a technically interesting but also serious problem, serious topic, right? Hypersonics. So I want to kind of frame up, what does it mean? Why do we care? Why is it a problem, right? So kind of capturing the title there, right? We're redefining speed, particularly surprise and deterrence as well. And when I say particularly surprise and deterrence, the reason I say that is, yes, we're redefining speed, but ICBMs have been around for a long time that fly at hypersonic velocities, but they're not maneuverable, okay? That's one of the things that really differentiates hypersonic missiles or vehicles, is that they're maneuverable at Mach 5 and above, and that's key, right? So that yields unpredictable trajectories, makes it extremely difficult for current defense networks to intercept or track and manage, right? In this case, for instance, it enables the conventional prompt global strike, against A2AD environments or heavily defended targets. But there's a pacing threat, though, too, right? So adversarial nations, China, Russia, and we'll talk more about that in a couple of slides here. They have operational and or near operational systems, and so we, the United States, we really got to hit the gas pedal, put the pedal to the metal, or balls to the walls, if you will, airplane lingo, to not only maintain deterrence, but really, regain kind of an overmatched dominance position, right, in later defeat options. So just another data point, when we're talking about hypersonics, it's generally stratified into 2 types of vehicles. You have what we call boost glide. So you have effectively a rocket boosted or rocket assisted vehicle that is launched up into low Earth orbit effectively, and then all the energy is injected into that vehicle through that launch phase, and then it glides back down. So it's boosted and then glides back down, and it maneuvers to target through that trajectory. And then you also have air breathing, which is generally in atmosphere. Scramjet powered cruise missiles is a good example. But both of these are maneuverable, and they both have their own unique challenges. A lot of the work that we do at Lift currently right now is mainly focused on materials and simulated, like physically simulated environments in. Oh, sorry. I saw your question pop up, Christine. But a lot of the stuff that we're doing is more relevant, not exclusively, but more relevant to air breathing hypersonics. But also we're stepping into some of the boost glide type materials and applications as well, which we'll kind of touch on a little bit. But hypersonics, why is it different, right? We all know the stories about the SR-71. If it's sitting on the tarmac cold, it's leaking jet fuel. It has to get up to temp to actually cause that thermal expansion of the body and start sealing up those joints so it no longer leaks. They actually have to refuel in the air, and then they're fine to go. So aerothermal heating, something that we're all familiar with, right? Well, aerothermal heating and just the conditions in general begin to change dramatically once you hit Mach 5 and above. So looking at the graphic on the right, don't spend too much time looking at it, but the idea is that you have a very strong bow shock. And that bow shock, not only it compresses and also heats that air in the bow shock region anywhere from 5,000 to 10,000 degrees Celsius. Technically, those numbers were Kelvin, but 273.15 difference, no big deal. In those conditions, the air dissociates and ionizes. So it's a plasma, right? So now you have non-equilibrium chemistry. It's a very aggressive chemical environment. That plasma sheath does a lot of interesting stuff as well. Of course, it drives oxidation and erosion. It also transfers heat to your surface, when the plasma recombines to the surface. But since it's a plasma, electromagnetic radiation can't get through it effectively. So it also disrupts communications and sensors and things like that. So another challenge, right? Now, it's not just materials, it's also communication, sensing, guidance, and so on. And, generally speaking, beyond the bow shock, on the leading edge or against the surface, you have this high enthalpy flow. Enthalpy is really just an idea of energy, right? Heat. Effectively, how much heat is in that local environment. And of course, you can discuss heat transfer and heat management, which actually is where we get into materials design and systems design. But either way, that kinetic energy that's imparted in the bow shock and ends up, moving up against your surface, a lot of that's converted into your surface, and you have extreme temperatures, you have extreme chemical energy. Your surface temperatures and the leading edges in particular can often get up above 4,000 F or more. I'm sorry for mixing units, but it's very aggressive environment. So the materials and the structures, they're exposed to what we like to say as extreme aerothermal mechanical conditions. Often we also use the term hot structure. So the idea is, think of the space shuttle. It has those tiles, those thermal protection system tiles. Those are meant to actually keep the structure underneath cool. So that's a cool structure. You can't really do that here in hypersonics. We actually, given the mass requirements and all other nuances for design, we actually have to tolerate a hot structure. So the structure itself is hot, and it's just a unique engineering challenge that we have to accept and manage, right? And then also you have transients, short residence times, extreme gradients. So on the digital side of things, modeling and simulation, you really have to have a robust multi-physics coupled approach to simulating these environments, the materials. You have multiple length and time scales all the way from the material manufacturing level all the way through structural and performance. But they have to be coupled though. So aerodynamics, heat transfer, chemistry, recombination, ablation, material response, and so on. So it's as I mentioned, it's exciting. It's fun to work on, but it's challenging. That's for sure. And that obviously then begets some serious changes as far as how we approach material selection and manufacturing, right? So really, the hypersonics necessitates a materials revolution. We have ultra high temperature capability requirements, high specific strength and toughness, oxidation and erosion resistance, shock tolerance, thermal shock tolerance. As I mentioned, weight matters, right? Mass costs energy, and so you can't just launch a tungsten vehicle effectively. I mean, it can be done, but it costs a lot of energy. And then just as important, or maybe even more important, is manufacturability at scale. So a lot of the material systems that are used are difficult to produce or take long times to produce. And later in this deck, we'll see that there's some interesting stuff that we're doing, and I know lots of people are doing really fun stuff, but we're trying to help reduce costs and accelerate the production of a particular CMC that we'll talk about. So there are some leading candidates, right? What we like to say UHTCs, so ultra high temperature ceramics. There's also UHT CMCs, so ceramic matrix composites. Of course, your standard CMCs that you see there, like silicon carbide, carbon SiC. Carbon's another one with the appropriate TPS, some refractory alloys, and then I mentioned TPS. That's where the advanced coating comes into play to manage the oxidation and erosion resistance. But there's a lot of maturation hurdles, right? I mentioned the predictive modeling of the material response and environment interactions, multi-scale, multi-physics, scalability, affordability, repeatability. Joining is also a big problem. That's again, interesting but difficult. Testing, right? Ground test infrastructure. It's expensive to do a live flight test. So having ground test infrastructure that can replicate sufficiently, combined environments for the given conditions that you're interested in understanding, whether it's aerodynamics and looking at shock fronts, or material survivability under a steady state high enthalpy environment. That you have to be able to actually capture those environments and make sure that you understand how the material is going to respond in that, and of course across those array of combined environments when you're in live flight, and then domestic supply chain, and then qualification and certification for flight. So all these hurdles are real. A lot of great work has been done and it's continuing to be done, but we need to hit the gas. And it's because there really is an existential threat, right? So there is an acceleration imperative for the United States to move faster. And this graphic here is actually from the Golden Dome initiative, and I've actually zoomed in on one portion of it there. First off, adversaries can hit us from around the world. Like, we have to accept that and understand that. We're even though we're kind of in a presumably, at least historically, safe space on the planet, that's no longer true. And looking at the top right there, China, one of the most common ones that we think of and focus on, say boosted hypersonic weapon. Currently, right now, they have roughly 600. 9 years from now, they're projected to have 4,000. Land attack cruise missile, currently 1,000. Projected 9 years from now, 5,000. So they're actually operational. And yes, we have I think maybe 5 or 6 programs of record as well. But we have to be aware of this. They're pushing hard. They're hitting the gas. And a side vignette, just talking about shipbuilding, for instance, the China State Shipbuilding Corporation, just to kind of again frame up adversarial nations. It's really it's not just a commercial shipbuilding industry. It's dual use, and they're putting, I forget the numbers, but they are putting, I think it's somewhere on the order of 1,000 times more mass into the ocean per year than we are. So hypersonics is a huge problem. Shipbuilding and sea dominance is another one. So yeah, we need to take this stuff seriously. Now, how, right? Like, what are we doing at LIFT? How do we actually put all this together, and how do we move the needle meaningfully in the setting of manufacturing and innovation as to where we're talking when working with our government partners, our industry partners, primes, whomever? That's kind of captured right here. It's maybe a little bit of an eye chart, but I'll walk you through it. I mentioned earlier, we have to have a problem to solve, right? That's where we come into the vertical there as far as requirements definition, right? So under requirements, first off, we have to have a problem. We have to have the appropriate, again, requirements, authoritative bodies associated with this. We also have to have the appropriate transition partners. Who has the need, right? And that actually bridges over to the far right side there for transition and supply chain. But we have to have all that framed up first before we bother to do anything, because otherwise, we're walking around in a dark room looking for the light switch. Once all that's satisfied, that's when we actually start doing the work, and we follow kind of your traditional development B, design, requirements, design, build, validate, test, etc. But we'll drop, we drop into the digital engineering side of things. That could be ICME, could be CAE, it could be connected shop floor, or otherwise, pretty much anything, depending on the problem. And then we'll do a lot of the design and optimization on the digital side of things, and then we'll actually pull the thread through the advanced materials and manufacturing process into the V&V. And V&V could mean, all your standard expected characterization and quasi-static mechanical tests, but it also could mean performance testing in a representative environment, hypersonic testing, high density flow, or high strain rate testing for munitions and shock events, things like that. But that whole package together allows us to run this whole design, build, test, vertically integrated workflow, where we can move much faster than maybe a set of discrete organizations, because it's all under one roof with the same team and a network of professionals and experts that many of you are all on the call, right? And I mentioned, I said design, build, test. We can also have some parity as well with materials, process, and applications. And we all love our acronyms: MIDAS, AMP, CERMAC, and HEAT. I'll speak to those in a moment here. And I'm going to skip the next slide because it's got some words on it. But what I just want to point out here as well is in each one of these verticals, take the advanced materials. I mentioned earlier, of course, we work in metals, right? We're foraying now into ceramics and CMCs. Actually, we've been working in that space for quite a while now on with some subcontract partners, but we're really bringing some of that work internal now, and we're going to continue to do so. And also the composites, right? So MMCs, CMCs, maybe some polymers and PMCs, depending on the need and application. As far as manufacturing, it could be cutting edge additive manufacturing, or it could be conventional manufacturing. Maybe machining is the right approach. Maybe castings are the right approach. So we keep all the tools in the toolbox, and we choose the right tool for the job. We don't want to just take that hammer and think that everything is a nail. And then the last comment about this slide is that we're integrating elements of AI pretty much across this whole workflow. And we choose the appropriate models based on what we're doing. A lot of it's, of course, going into the digital side of things. Could be physics-informed neural networks. It could be large language models or whatever. I think I have a slide on that as well. But lots happening. But generally speaking, this captures our tech pillars and approach to problem solving. And like I said, there's a bunch of words here. You can look at this at your leisure when these slides go up. So I mentioned those acronyms and differentiating capabilities. Really, that's what they are. At each one of those nodes and those verticals on the tech pillars is a packaged set of capabilities with a defined intent. And I have slides in more detail on these, so I'm not going to dwell on them here. But MIDAS means the Materials Informed Digital Acceleration Suite. AMP means the Advanced Metallics Production and Processing Facility. CERMAC you can think of as the analog, the ceramics and CMC's analog of AMP. So and then HEAT is the Hypersonics and Extreme Environment Testing Facility. So MIDAS is build, MIDAS is design, AMP and CERMAC are build, and then HEAT is test or BNP. Okay. So MIDAS, just a couple slides. Anchor point, this is where we are, right? Digital engineering side of things, although again, it interacts and connects with the whole rest of the chain there. So most of the time when people talk about integrated computational materials engineering, and let me pull up really quick. As we go through these, I don't want you to don't think about lift, right? Think about problem solving in the setting of hypersonics and extreme environments. Like how are we designing new materials fit for purpose, or solving problems fit for purpose, whether it's materials, manufacturing, they go hand in hand. And when we see these slides, think about the intent of them to facilitate finding solutions for those types of problems. Okay, on the modeling, simulation, or analysis side of things, there's all kinds of different solvers or codes or softwares that do things, right? And we love our fundamental materials and manufacturing relationship spectrum, right? So Normally people just say process, structure, properties, performance. We actually like to interlay geometry and chemistry ahead of process, because your geometry and your chemistry are going to feed into your manufacturing process, and your process and associated thermomechanical history with that chemistry and geometry, that's going to drive location-specific microstructures, which then feeds forward into properties and performance. And so it's all interconnected. And you have codes at each one of those nodes. And most of the time, as a general rule, those codes don't talk to each other. So most of the time when people are doing ICME, they're actually doing CME with manual transfer and handoff between the different codes. Well, that's a huge problem, right? And we recognize that at Lift. And so we built Midas deliberately to solve that problem. So Midas, as I mentioned, stands for the Materials Informed Digital Acceleration Suite. You can think of it as a digital commons or a virtual commons that allows you to plug and play disparate or disconnected software and make them talk to each other. You can think of it as middleware. But the idea is that really it enables ICME. It puts the I in ICME. It enables a materials-focused, multi-length scale, multi-time scale MDS approach to materials and systems design. And so it really is an enabler, and it's a software agnostic approach. You could choose NX, CATIA, whatever. You could choose your favorite CalFAD model, and it will. You can set up an automated DOE on the front end, hit go, and it will go through, execute your simulations and software A. It'll extract, post-process, and translate, pre-process, handle all the units, upload to the next software, execute, and chains back and forth. So eliminates unit conversions, human error, accelerates things, and then again that allows us to really run design of experiments and optimization routines, and really truly drive ICME. So that's the intent of Midas. Of course, we also use ICME and we use Midas to do a lot of the simulation work as well across that whole spectrum, and we'll talk about that in a little bit here. So of course, if you can accelerate things like that, with ICME and the whole design side of things, predictions here or projections really show that if we have a fully automated ICME approach across that whole spectrum there, you can actually drop, say, an alloy development schedule anywhere from 60 to 70% of the original time required and 50 to 60% of the cost. So there's value there too, and this helps us to move fast. Quick comment as far as connected shop floor and mission control. In that whole building, we have a bunch of equipment. They have sensors and process data and all that. We're connecting all those systems and their associated data streams into our mission control through our servers and HPCs. We have dashboards that we display. We can look at real-time data. We can also interrogate those data streams with our ICME models as well, and really make that robust cyber physical connection. So there's a lot to say there, but there's not time for it. So AMP, again, in the setting of problem solving for challenging challenging environments, we're talking about build now, right? We talked about the design, now we're talking about build, materials and manufacturing process. And what we found is that I can buy a crucible of novel powder or novel material, whatever, from academia. I can buy a truckload from industry, but getting that development middle scale volume is very difficult in the United States. And so we recognized that, validated that reality, that challenge is a reality, and if it's perfectly within our charter as an institute to stand something like this up. So that's what we did, is actually stood up the advanced metallics production and processing facility so that we can produce development volumes of custom alloy feedstocks and say powder, wire, rod, bar stock, castings, et cetera. And the idea is that it's roughly speaking, with some asterisks there, we can alloy just about any metal in the periodic table. We can make powder with just about any metal, any non-pyrophoric wire, so on and so forth. So it's to help fill that gap again, that 4 through 7 space. That's our charter. That's where we belong, and we're manifesting that in the physical build side of things. So also have a lot of actual part production capabilities here. So powder bed fusion additive systems, 1 kilowatt M290 as well, just to call that one out. I would say world-class multi-wire plasma arc welding DED cell for large format builds, a whole bunch of other stuff, extrusion presses, friction welding, other presses. It's a big kid's playground for sure. So if you haven't been to Lift yet, please visit us, come see what we have and how we can help you. And then just a couple distinct call outs here. So 250-ton DCS press here for direct current sintering, and then the plasma arc welding DED cell. So we can do high build rate type stuff, 40 to 60 pounds an hour. We can run anywhere from 2, 4, or 8 wires into the melt pool simultaneously. So we can either do online alloying or spatially or functionally graded materials. So again, the functionally graded type capability actually maps into things like leading edges or kind of graded structures that are more appropriate for challenging environments. And then I mentioned earlier, like comprehensive laboratory services, all the standard things that you would expect. Ceramics and CMCs. So again, this is a build side of things, and I'll talk about this quickly here. So CERMAC is the high temp materials analog of AMP, and our inaugural project that kind of nucleates CERMAC, we're looking at some process and material selection modifications to lower the cost and accelerate the rate for production of graphitic carbon-carbon. Looking at low viscosity resins that are graphitizable, they're actually thermosets, so we have rigid green parts we can take out, go straight to pyrolysis, and so on. And we have some process mods that we're looking at on the heat treat side of things as well to accelerate. So early stages of that project, keep your ear to the ground as we move that forward, but very excited about that. And then heat, right, the testing side of things, V&V. So currently we're standing this up at LIFT in Corktown. Eventually this set of capabilities will end up going to Sulphur Air National Guard Base in Michigan. Broadly speaking, we're talking about high enthalpy sustained hypersonic testing up to Mach 8, so Mach 4 through Mach 8, say minimum runtime, matching enthalpies, to the actual Mach number. We can simulate different altitudes. And the intent here really is material survivability screening and increased access to this type of testing capability, because the current infrastructure in the United States is quite strained, right? So it might take a year to get on schedule at AEDC. Ultimately, the materials are still going to have to be tested at AEDC, but you can at least test and screen your materials with us ahead of time, and because we can hit similar conditions or even higher, and you can kind of see that on the graphs on the left there. So, so yeah, high enthalpy sustained, high pressure, high temperature, up to Mach 8 testing with a wealth of in situ data that we can collect as far as thermographic, chemistry, pressures, you name it. And then the other side of things is more relevant to munitions and armor, basically high strain rate type testing up to 10 to the 8th in modified environments, right? So that's the heat side of things, and I've got 15 minutes left, so I think this actually worked out really well here. So why do we care about all that? Yeah.
Let's launch a poll right now as you transition, as you kind of just talked about that heat. I'm going to launch this poll so we can understand what the audience is experiencing. So it's launched. I want to make sure the audience sees it. When it comes to Hypersonic Systems, which best describes your organization's current role? So it looks like I got some 25% participation for all those that are listening. If you could give it a minute. And then I do have another one as you transition to some of the other presentation, but we'll let this
interrupt me whenever you want. No worries. Just tell me when to stop. So, we've framed up LIFT, why we exist, framed up the problem as far as hypersonics, why we care, what are the unique challenges, our approach to problem solving, the associated set of capabilities in the setting of a National Manufacturing Innovation Institute that we've built and stood up to address these types of issues. And so what, right? Well, I'm just going to give you a quick example here, how we've exercised that full workflow. We're not going to cover all of it, but that full workflow where we've ran the digital thread from, across the whole spectrum, all the way from, short length and time scales at the materials level, all the way through the performance level, and ran that hand in hand with the physical activities, making materials, making parts with materials, testing materials, and validating and calibrating those models all the way through to bring us to success for specific need, right? Now, a lot of this work is CUI. What we're sharing here is distro A, approved for release. So there's a lot of fun stuff that we can't share, but the idea is that, I mean, it's effectively captured in the title here, right? So an experimentally coupled hypersonic digital twin to scale material solutions. So the idea is that the take-home message is we now have a digital twin, a multi-length scale, multi-time scale digital twin from the material level through the manufacturing, property prediction, performance prediction, all the way up to the test in a Mach 5 reacting flow environment, and the physical capabilities paired with it ran all the way through. So in this case, the objective here, right, we were looking at developing some novel high performance alloys that were suitable for hypersonic applications and additive manufacturing. Could be skin, could be structure. These materials were not really leading edge materials, although they actually survived quite well under Mach 5 flow. But also, again, to develop this ICME workflow across that whole spectrum of these additively manufactured materials for this application here, and of course run the verification and validation of these materials in the appropriate environments. So let me see here. I just want to thumb forward quick. Yeah, we actually left out the material identity. Okay, those of you that are metallurgists can probably pick this one out. But anyway, one thing I want to say, so there's actually multiple material systems that we investigated here. One of the success stories that came out of this, we actually wanted to modify a COTS alloy to make it more printable for additive manufacturing and also mitigate the need for post-built heat treatment. And we did that successfully. We made that alloy and made parts, tested the parts, all your quasi-static testing, stuff like that, but we also tested them in a real environment. So there actually is a real success. There's actually multiple success stories in this, but either way, what we're going to do is we're just going to focus on a couple elements of the scope of this project here. So, the microstructure simulation, 3D printing, in this case, powder bed, and then also really the hypersonic performance simulation. So we'll eliminate the geometry, structure properties, etc. But of course, all of that was a part of it. So thinking about the microstructure, I mentioned chemistry, process, structure properties, performance. Your chemistry moves through your manufacturing process, and that's going to impart those together. Will end up yielding a location-specific thermomechanical history, which things like solidification rates in the chemistry as well will yield your microstructure, which then of course drives properties and all the other fun stuff. So how do you predict your microstructure? Well, one of the ways that we approach that is through phase field modeling. There's all kinds of interesting things about it. There's good things, there's challenging things, etc. But this is what we leveraged and used is phase field modeling. So I'll draw your attention to the bottom kind of right there, that black thermal history trace. What that is actually a real trace of our additively manufactured build. You can see some of the thermal cycling there early on. Through the build, taking the build then out into stress relief, and then subsequent set of heat treatments and annealing. So that's the full thermal history of post solidification thermal history of those parts. And we then took that thermal history and coupled with our phase diagram, CalFAD models, and the phase field code, and we're able to go in and actually simulate our microstructure evolution, through the powder bed, heat treatment, and all that. Begin to identify the presence or lack of deleterious phases, observe and predict grain growth, and so on. And we actually got very good agreement, pretty much across the board. So we were quite pleased with that. But it doesn't always work. The same is true for crystal plasticity. For instance, if you're talking about property prediction from microstructure, works for some crystal structures and not well for others. But either way, we were very pleased with this. And then looking at the macro scale level simulations here, what we're really talking about is the powder bed fusion and also the test, right? So on the left there, we're simulating the powder bed fusion and heat treatment. So it's effectively a thermal FBA type simulation coupled in with our phase build and CalFAT codes. And the goal there was really to extract location-specific thermal histories and residual stresses. And one thing I didn't mention earlier about Midas is that it doesn't just pass models back and forth. There's a web and thread of connectivity across all those models tied to the geometry. So we can define a matrix of locations on a part and track them from code to code to code. So we have this point tracking capability that we can carry all the way through, so we can actually audit on a location-specific basis. But again, we did that. We can predict, of course, residual stress and temperature and all that, align that against our physical results. And then in the hypersonic test, so again, we're talking about a Mach 5 reacting flow test, similar to what we're setting up at Lift. And we use two different codes to predict the aerothermal environment in the setting of these wall-mounted, in this case, samples here. And you can see the results are quite different, right? The one on the left, temperatures on the scale are very high. The one on the right, a little bit more realistic. And the one on the left is actually a hypersonic code. We're redacting it just because we've actually worked with them to solve some of the issues there. But not all codes are created equal. All models are wrong. Some are useful, and so you have to be careful about that. But the code on the right actually had great agreement with our empirical measurement in the live tests as far as temperatures and pressures and so on. So, and then COTS and novel alloy powder, as I mentioned, that we worked with a couple different alloy systems. So we benchmarked against the COTS. We also modified the chemistries to be more printable and mitigate some of the needs for heat treatment. We did that in Midas. At the time, AMP was not commissioned, so we actually had that full processed, and that was quite a challenge. And then, of course, you validate the chemistry against the spec and, measure all the particle sizes, et cetera. So then we had powders. We made parts, as you saw on the prior slide, and what you see here on the next slide. We ran it through the manufacturing process, right? So in this case, we actually just used your standard ubiquitous 400-watt M290 and made a range of fracture toughness or Sharpie samples, tensile bars, I think fatigue as well. We looked at uniaxial, rotary bend. What else? I don't know. We did a bunch of fatigue testing as well. And then, of course, your wall-mounted samples that you see on the bottom right there. And, notice they're built upside down. I mean, it makes sense, right? It's additive manufacturing, but that's part of where the point tracking comes into play, because as you're passing your geometry model through your digital thread in the modeling and simulation space, you have to be able to flip that model over and understand that now the point's over here. Now it's going to be in a different environment, and it's there's going to be different heating curves and so on. So ran that all the way through, followed all the ASTM methods, right? Stress relief, YAD under removed specimens. We also hit solution yield and aged, and then brought this into the physical test. So you can see CFD1 was the one that it's a density-based solver, had some issues predicting way higher temperatures than we expected, but CFD2 did a great job. It was pretty much spot on with the test, which are the red dots. So steady state was not fully achieved, although we're pretty close though. We're starting to asymptote there. As far as the temperatures, pressures were probably steady state at that point for sure, but temperatures were not. And then we carried these results from CFD1 back to the software vendor and actually brought them value and identified some challenges and issues. And I think that we've been able to course correct with them since then. So part of the way that we work with our partners and help to bring value. So, but again, this all relates to the handshake between the digital and physical and building that digital thread all the way through. So, and then post-test evaluation, you're going to do some sort of a live test. You want to look at ablation, right? Any sort of microstructural changes based on heating, cracking, etc. We didn't observe any porosity or cracking. There were some regions with higher heating, so say locations 2 and 3. We did observe some coarsening of the precipitate phase, and found that really by EDS. That was a niobium-rich phase. And it was, of course, in alignment with our other partners' findings as well for some untested specimens too. So yeah, I think there's an error there. Actually, that doesn't make any sense. I believe we did actually see some coarsening, and that would be based on heating, right? But all that data feeds in. We are working on integrating chemistry and ablation codes into Midas as well. We're not quite there yet. We know what we want to integrate. We actually have the codes, and we just have to actually get the hooks for the software into Midas. So we're building Midas every day. We're building our physical capabilities every day. Again, the intent is actually to solve hard problems that material solutions and manufacturing for hypersonic. So, and then kind of like transition story here, right? Their scale of story. So the test section for the samples that we were making is roughly a 2-inch by 2-inch exposed area. That means the samples are limited in size as well. It's a little bit difficult to instrument them, and of course, there's optical imaging and inspection that you can do as well. But we're building with Kareem on that at UCF a larger version of this test chamber at lift, as I mentioned earlier. I already really gave you the figures in there, Mach 4 through 8, up to roughly 3,500 Kelvin stagnation, 170 atmospheres stagnation pressure, and it's effectively a continuous runtime compared to, say, shock tunnels and things like that, where you get 10 to maybe 20 milliseconds of data. So, pardon me, that will be online mid-2027. It's meant to be an extended workbench for anybody on this call or otherwise, and so that's why it exists, right? Is to help accelerate material solutions and make things move faster, make things faster, better, cheaper. So this is how it all integrates, right? Digital, advanced materials, manufacture, process, V&V, scale up and commercialization. And really all of that is facilitated by these carefully chosen and developed differentiating capabilities that really complete that design, build, test development fee, if you will, right? So Midas, Ceramac, and heat. And in doing so, we like to call that ATOM, right? Because it allows us to accelerate the development of advanced materials. So it's a vertically integrated stack of capabilities. All the team members are vertically integrated as well. It's all co-located, and so that's really what ATOM is. And it's really it's an ecosystem, or it's a network, I should say. It's scalable, it's replicable. We have a range of important stakeholders, key stakeholders, authoritative bodies, suppliers, government partners, and so on, TRMC, et cetera, you name it, all working together. And it's in service of solving problems like hypersonic materials. So that again is the whole setting of this talk is what are the challenges that hypersonic environments present? How do we respond to them? How do we relate that back to adversarial risk and national security? And what at LIFT are we doing to help move that needle? And so that's how it all comes together. So with that said, I appreciate your time. Thank you for listening.
Yeah, I'm sorry. Let's launch another poll right now. What I want to talk about is I'd like to understand what the audience feels is the most critical need to de-risk these materials and manufacturing programs. So I'm going to launch the poll. So for those of you that are on, and as John shared what we're doing, I'd like to understand what is critically needed on your end.
Yeah, I mean, for those of you that operate in this type of a space, whether it's hypersonics or other extreme environments, what are your biggest challenges? Is it qualification? Is it materials and manufacturing? Is it collecting process data to facilitate either optimization or drive decision changes? What's important to you?
Thank you. This is some good stuff. I got a lot of good participation. Very valuable. Thank you for your insights. I'm going to end this poll, and then based on what John shared, with the group, I'm going to launch another one. So how likely is your organization to use Lift, what you've learned today with all of our technical capabilities? So help us understand where there might be alignment, collaboration. So I'll launch that one.
Yeah. And to piggyback on that, I guess as you all are thinking about the question and responding, you know, we're a National Manufacturing Innovation Institute. We're in a pre-competitive space. That's the public-private partnership. We're an extended workbench, right? That cares greatly about this nation, about what we're doing. We're passionate about it. You know, the Midas side of things, you know, I used to run the physical exclusively, and a counterpart of mine ran the digital, and I always joked that her job was to put me out of a job, because eventually our intent is to try and get to the point where the digital side of things is so effective that you only need to make one part, right out of the gate. So, and that's where we're driving with Midas, really is headed toward that direction, right? So virtual pilot plant, virtual digital twin for every part, you know, board certification, and it's a lofty goal, but we'll never get there if we don't continue. But the idea is see us as an extended workbench. Our reason for being is to facilitate and assist, and so, you know, I mean, we're going to keep going on our own no matter what and solve the problems, but we'd love to help you solve problems too. So.
Appreciate that. We've got a question coming in regarding Midas, when the product would be available. I think you shared kind of the timeline and our plan for that. So if there's a specific question, John will take, or as that specific question, John will take that offline. We will, this presentation will be distributed after this. So I appreciate everybody joining. If there are any other questions, I will take those now. Otherwise, thank you, Dr. Keel, for a fantastic presentation. It was very insightful, engaging. I appreciate everybody's participation, and as we activated those polls, we want to understand your perspective. That's why we exist. So it's very important to us. So thank you, everybody, again. Thank you, John. Mark your calendars for our next Liftoff webinar, March 25th. Appreciate everybody joining us today. Have a great day. Thanks
everybody. Appreciate you spending your time with us.